Hi again, science students. In this video we're going to continue our discussion of projectile motion, and we're going to focus on time of flight. Now this person is dropping and projecting oranges off a ledge, obviously trying to make orange juice or marmalade or something like that. But the important question is which of these oranges, whether it's projected horizontally or if it's just dropped, which will hit the ground first. But you might like to think about that for a moment and pause the video. Then I'll show you another video, and it is this one here, in which I will demonstrate. So I am going to project. You can see I'm projecting one ball to horizontally and dropping the other one at the same time. Which one hits the ground first? Pretty much at the same time. Let's have an action replay. Here they come. And they hit the ground pretty much at the same time. Okay. Righto. So let's can the action replay and write this down. They hit the ground simultaneously. I'll just write at the same time. Hit the ground at the same time. Okay, now, how long does it take each orange to hit the ground? So they're going to hit at the same time. All right, now this is going to be important for us because what this means for our horizontal projectiles is that they have the same flight time as an object that is dropped. Okay, so we're not even going to worry about the horizontally projected one. We're just going to worry about this one that's dropped. So you might want to take some time here to pause the video and write down that magic word, which of course is suvat, and see if you can figure out how long it takes for this first orange to hit the ground. Okay, so I'll try it now. The height is 3 meters, so that's our displacement. If an object is dropped, it starts at 0 meters per second. We're not really interested in this. The final velocity, we know that it'll accelerate towards Earth at 9.8 meters per second, and the time is what we want to find. Okay, so now that we're using that equation, which is S equals ut plus a half at squared. Now we want to make time the subject of this equation, but as discussed, that's not possible to do unless, of course, u being 0 makes that term disappear to 0. So we get that S equals a half at squared. And as discussed, this rearranges to this, which is extremely important, that equation. And if you practice enough, you will start to remember this, this off by heart. That one I'm just trying to highlight there. Okay, so I'll just do a little calculation because I'm running out of room there. Just do a calculation here. The time taken to hit the ground is equal to the square root of 2 times the displacement over 9.81, the acceleration. So that means it takes over 9.81, 0.782, we'll say, 0.782 seconds. Okay, so well done if you got that. Okay, now, we're asked how far does the second orange land from the ledge? So we want to know this distance horizontally from the ledge. Okay. So I'll call that Sx for our horizontal distance because x is the horizontal plane. So we know now that the time of flight of this second orange is the same, 0.782 seconds. It's the same as that. All right, but remember we're talking horizontally, so we're using this equation, S equals V times T. Okay, so we know the time of flight is the 0.782. Where's our velocity? Well, that's the horizontal velocity that it was projected at, 7 meters per second. So that doesn't change throughout the flight. So this is equal to, it's going 7 meters per second for 0.782 seconds. So 0.782 times 7 gives 5.474. So the first calculation was to do with the vertical plane, so we used SUVAT. The second calculation was to do with the horizontal plane, so we just used that simple formula regarding displacement, velocity and time, non-accelerated motion. Okay, so go ahead and try the other questions about the plane with the bag and the stunt director, or the director of a movie with a stunt person, and have a look at those solutions on Canvas. Thanks for watching.